Good afternoon, everyone. Hope you guys had a nice weekend. Um, Welcome to lecture 27. So it's going to be an interesting one today. So today is on non-circular internal flows, but that's really only going to be about half the lecture because non-circular internal flows get a little bit more complicated, and we're not going to look at them that much in this course. So I'm going to spend some time on non-circular internal flows, and then I'm going to do a demo with the circular internal flow that'll help us practice using the modified Bernoulli's equation to predict flow rates. So I mean, non-circular internal flows are quite common, as you see here. Some ducting. I would say that's the most common application. Maybe can anyone think of an advantage of a non-circular cross section versus a circular cross section? Maybe within the context of HVAC. Why are ducts square? Yep.
Get away from boundary layer.
So maybe in terms of flow rate efficiency. Okay, that's an interesting one. Yep.
Easy to tube into a square building.
Exactly. So the buildings are square, right? So square ducting, if you have a certain volume of air you want to move, tends to be more spatially efficient, but circular ducting is better for losses actually than squares. Um, what about in terms of why don't you think they build square pipelines? Why are pipelines around?
Much losses.
Sorry,
Not strong.
strength. Yeah, sorry, is that what you're going to say? Yeah, strength. So the circle is a really good shape to be able to take like a high pressure. If you try and put that pressure through a duct, you get like the concentrations in the corners, the thing will rupture more easily. So for high pressure stuff, you use circles, and for more spatially efficient stuff, you can use rectangles or squares. So um, any other design advantages? I think um, so they're easier to work with, yeah, in terms of like flat sheets and stuff like that to make a square duct. That being said, round things are also pretty easy to make. Like pipelines are, the manufacturing is relatively straightforward. They basically, I think the default procedure is they just take a flat sheet and roll it and then put a seam down it. But there are many different pipeline manufacturing methods. So yeah, we're not going to do turbulent flows in ducts. So that gets into more of the realm of HVAC and that sort of thing. But we're going to see how laminar flows work in ducts today. Reminder, so last lecture we developed the extended Bernoulli's equation. That equation is given here. It's been extended in a couple of ways. So we now account for frictional losses, aka viscous effects. And we don't restrict this along a streamline anymore. So this is more of an averaged cross section that our extended Bernoulli's equation applies along. So we have pressure form in the top there. So every term in the equation has units of pascals. We also have head form. So every term in the equation has units of meters liquid. This alpha here that multiplies our kinetic energy term is a correction factor to account for the fact that the average energy of sort of our streamlines, the square of that, isn't the same as the square of the sum of each individual streamline squared. So that's just a switch. So we just know the value of alpha if we have laminar or turbulent flow. Okay, we're still talking about extended Bernoulli's equation today. So our learning objectives are to compute hydraulic diameter for internal flows, calculate friction factor or read friction factor off a table, more like it, for laminar flow in a non-circular cross section. I'm going to give you an overview of the actual different types of internal flow problems that you can be asked, and talk about which ones are more complicated to solve. And then we're going to do a prediction. So we're going to do an example using a circular internal flow. So just a small bit of non-circular stuff in this course in general, just to kind of expose you to that. Okay. So just as a circular cross section has diameter, a non-circular cross section has a hydraulic diameter. So it's kind of a pseudo diameter. So usually we see the term hydraulic diameter in non-circular cross sections. So the hydraulic diameter is calculated like this: 4 times the area C, so the cross-sectional area, over the perimeter of this cross-sectional area. So say we have some sort of rectangular duct like this. The perimeter is given there in red, and the cross-sectional area is this area here in the green. So when it comes to non-circular cross-sections, you might come across this in later courses. It's always characterized in terms of this hydraulic diameter. So it's like a diameter. What's the diameter of a square duct? That's what this is. So we can compute this. For example, for a circle, the hydraulic diameter of our circular cross section is 4 pi over 4d squared over pi d. So that's good. So for a circular cross section, our hydraulic diameter is just the diameter. Okay, so this AC is pi over 4d squared. It's the area of a circle. And then this pi d is the circumference. So that's the length of the perimeter of the circle. For a rectangular duct, the hydraulic diameter, say we have a rectangle with two sides, A and B. The area is AB. So we get 4AB over 2A plus 2B, which is 2AB over A plus B. So this is a geometrical property, just in the same way that the diameter of a pipeline is a geometrical property of the pipeline. Now with this hydraulic diameter, the reason that we want to talk about hydraulic diameter is so that we can reuse as much as possible that we've done so far. So all the calculations have been in terms of diameter. So we're going to keep using that in our calculations. So we have a Reynolds number based on hydraulic diameter, which is rho v average dH over mu. And we still get m dot is rho v average A. So that's the same. For, oh yes, do you have a question?
Yeah, I was just wondering, what's the starting, derivation, 4a over p just seems so, clean. I don't know.
Yeah, it is clean. I agree. It's a clean formula. I think part of this is so that we get diameter of a circle when we plug a circle into this.
Yeah.
So it's sort of because we feel like the hydraulic diameter should depend somewhat on the area, maybe somewhat on the perimeter. So if you have some really wonky shape, um, yeah, so I'm not sure the starting derivation of this, but you're right, it is a straightforward thing to calculate. Okay, so there's our Reynolds number based on our hydraulic diameter, mass flow rate. In fact, the Bernoulli's equation, the extended Bernoulli's equation can still be used with non-circular cross sections. The tricky thing as always is the friction factor. So the friction factor is a little bit different. It still allows us to characterize the pressure drop in our non-circular cross section. I'm only going to do laminar friction factors for non-circular cross sections. So does anyone remember what the friction factor is for a circular pipe for a laminar case? Yep. Yeah, other way around, but 64 the Reynolds number. So we said that for laminar flows, the friction factor generally depends just on the Reynolds number. Surface play a big role because the diffusive effects are so high that the perturbances caused by sort of the surface roughness are easily sort of diffused away by the viscous effects. So this is still the same. So our friction factor is still a function of our Reynolds number. Just to be consistent, I'm going to call that Re sub d. And so we should use this table 8-1 from the Sengel book. So I'm going to, once you finish writing that, I'm going to show you what this table looks like. So I posted this on Learn. So this is the table down here. Okay, so the first thing we have is the circle. So again, 64 over the Reynolds number. For the rectangular duct, we get different friction factors depending on um, the cross-sectional area there. So this is for laminar flows. So yeah, you can see here that depending on the aspect ratio, so for a very wide duct, you get basically your geometry will tell you what your friction factor, what coefficient it is over the Reynolds number. Same thing with an ellipse. So you can see the two sides of a rectangle are A and B here. And we've seen how to calculate the hydraulic diameter for that. We also have, I don't think triangular ducts are very common, but laminar flows go through all sorts of weird cross sections. So the microfluidics side of fluid dynamics has very well characterized laminar flows. There's a whole kind of branch of fluids that are just, and since the scale is so small in these microfluidic devices, it's all basically laminar flow. So if you're doing flow at that scale, um, it'll be very well characterized, basically the flow through those cross sections, or very easy to simulate, because laminar flows are generally more easy to simulate than turbulent flows. So any questions on using this table? Once you get this friction factor, once you get your Reynolds number, it's basically the same analysis as circular stuff. Yep.
Just like once the ratio gets large enough, it turns independent.
I think so. Yeah.
Because it goes to 8 and then
You know, I've actually never noticed that on this table, so I don't know what it infinitely. So that's what an extremely thin duct. That's kind of the limiting case, I guess, right? Yep. Did you have other questions? Same one?
Yeah.
Yep.
Why is it the how does the angle affect for the triangle? How does it affect? Is that because like the different angles, if it's sharper, it has more of a boundary layer effect, or like how is the angle kind of because it increases up to like 60 and then begins to decrease.
That's a good observation. Also, something I haven't noticed in this table. So clearly, I haven't. You've already studied this table more than me. I'm not sure what the mechanism is happening there. To be honest, why it would be. Yeah, I would be like that. Any other questions? No. So this is basically a lookup table once you calculate your Reynolds number. Okay, so I'll move on now. So I will maybe make a comment. Again, it's not part of this class, but the HVAC design textbooks, HVAC design guidelines, all that is full of these friction factors for different ducts. So it tells you roughly how much pressure drop you can expect at this duct, with this material, this velocity, that sort of thing. So this is just to kind of show you how roughly it's done. Um, but again, in your if you say work for an HVAC company in practice, you'll see they have huge, books full of this stuff. It's all just basically friction factors based on the geometry, material roughness, that sort of thing, though. Okay, what about the types of internal flow problems? Okay, so down the extent Bernoulli's equation here. So P1 is 1/2 alpha 1 rho V1 squared. So rho GZ1 pump. Yes, our losses in our extended Bernoulli's equation are where a lot of complications arise. Okay, so the variables we have for internal flow problems are these are more the engineering design variables of interest. So the volumetric flow rate is an important one. So the HVAC design criteria will tell how much volumetric flow rate is in the room. The volumetric flow rate tells us like how long we want a gas pump to fill up a car. Volumetric flow rate is everything. So volumetric flow rate is an important one. We also have the diameter of a pipe. So I'm going back to circular flows here. So the diameter of, say, a pipe, the pressure drop along our pipe or duct or whatever it is. Sorry, is that too messy for you guys to read this stuff? A little bit? No? Okay. This is FL over D rho V average squared over 2. So that rho V average squared is in a couple of that stuff there. Okay. So we have volumetric flow rate, diameter, pressure drop. Those are the three big ones. And the rest of these are usually fixed. So we don't have much engineering choice over the density of, say, the fluid we want to sell or the viscosity or the length is, we have some influence over the length sometimes. These are roughly all the variables we have in this problem. So the three types of internal flow problems are characterized by what we have and what we want to find. Okay, so a reminder, the Reynolds number is rho V average D over mu. Friction factor for most cases is a function of Reynolds number and surface roughness. So that's for a turbulent case. Sorry, are there any questions about the equation? I apologize for the messiness. Yep.
Is it Z instead of G for a variable? Like, are we considering gravity constant here?
Yeah. Yeah. So I guess Z would also be one in here. Well, that's kind of the geometry. So L, maybe we also have Z, but yeah. So that I guess Z is also a variable we have to consider here. Usually what happens when we design like a ducting system or a piping system are we want to connect something to something. So we're ultimately working with some certain delta Z that we have to account for in our system design. Okay.
So,
Yep.
why is G a variable?
Well, it's usually fixed. Technically, it appears in the problem, but yeah, you're right. We usually don't have any influence over G whatsoever. It's something that we have to consider in the problem. So I'm just trying to list everything that appears in this problem that's non-unique. So for example, if you have diameter, you can figure out your volumetric flow rate, that sort of thing. Yeah. So there are three types of internal flow problems. It will maybe help you approach the problem before you start solving it, figure out which type of problem it is. So we'll call it problem type. The first problem type is where we have specified some volumetric flow rate and a diameter. Okay, let me just clarify. So these will pretty much always be specified. Yeah. So if you're specified a volumetric flow rate and a diameter, and you're asked to determine the pressure drop, that's basically what our formulas for internal flows are designed to do. So they basically take those as inputs and give you a pressure drop as an output. So that's the easiest type of internal flow problem. So I've done several of those examples. That's also what you did for your tutorial, I think. So I gave you volumetric flow rate for, I think, a couple of the tutorial problems. So that's the easiest one, and that's because it's a straightforward kind of plug through the equations. So if the second type is we specify the diameter and the pressure drop. An example of this would be, say we know what pressure drop our fan or our pump or our energy source can provide. We want to know with that geometry and that pump how much volumetric flow rate we can expect in a system. So if we're asked to determine the volumetric flow rate, that gets a little complicated. So the example we're going to do today is going to be an example of this. The third type is the most complicated. So in that case, this is like a sizing problem. Yep.
Stick your variable. Is delta P you're changing like the P1 and P2, or is it delta P?
It's kind of both. It's just a general, yeah, pressure drop relationship of pressure in our system. Yeah. Don't think too critically about the actual variables and stuff I'm doing here. It's more about what to determine. If we're trying to determine the pressure drop, that's easier. If you're trying to determine a volumetric flow rate given those, that's a little harder. And the hardest one of them all is to determine the diameter that you should be using. So if you're given a volumetric flow rate and a pressure drop, determining the diameter is complicated. And there's an example of this on homework 7. Now, the reason that it gets more complicated is it's because the number of variables that depend on each other in all of our equations we have here. So everything depends on diameter. So that's why it gets the most complicated when you're asked to determine diameter. So the students like before you and before basically having access to computers, this was like an extremely difficult thing that they would have to do. So they would have to iterate through all these because you need to know diameter. If you know volumetric flow rate, you need to know diameter to know velocity, and then you need to know diameter to do all the other things. So what they used to have to do is pick like a diameter and then iterate, iterate, iterate. So they pick a diameter, get a friction factor, get a delta P, and say, oh, that wasn't the right delta P, so I have to keep iterating. But nowadays we can just use a computer to solve all the equations simultaneously. So that's what I'm going to do in the example today. So this is where the original 3 classes of problems come from, because there's different strategies they used to use for solving them. The difference here today will come from our just the form of basically the amount of complicatedness of the equation that we have to solve at once. So yeah, if you want an example of the third one on homework 7, there's an example of that where you need to use like some sort of computer to solve the equation because it just gets too complicated. Yep.
Would it get even more complicated if you tried to do a problem with some of the specified variables?
If you're trying to like identify the fluid that can be piped through this system or something like that.
Yeah.
Oh yeah, yeah. It gets even harder, but um, at least nowadays you guys have access to Excel and computers and stuff like that. So they used to have to do this type of analysis by hand. Okay. So basically, when you're asked to determine one of those 3 variables, that's the level of difficulty you can expect in the problem, the level of ugliness that the equations become. And it's mostly because that friction factor is kind of an ugly form. Okay, so we're going to do an example now. So we're going to estimate. So this is something called a siphon. So the problem we're going to try and do today is estimate flow rate through a siphon. So the diameter of this is given here. Okay, so I'm going to set up this demo. So here's some kind of material properties that we're going to use and the diameter of the tube that I'm going to use. So set this up. I have a leak somewhere. Okay. So this is an extremely complex experimental apparatus. No, if you get splashed, then something's gone really badly. Okay, so I have a big tub of water, maybe just in case you get wet. Okay, so I'm going to set up the geometry, and then we're going to sketch it versus I think it's a little bit more valuable if I set this up and then we sketch it and analyze it versus just starting with the sketch. Okay. Yeah, sure, no problem. So this is, say, a reservoir of water. And what a siphon is you may have heard of, some people use this to steal gas, which is not something you're allowed to do after I teach you how to do it. It's only for emergency purposes, so you have to move gas between vehicles or something like that. But actually a siphon is like a very classic like fluid mechanics thing. So this goes like way back to Archimedes and things like that when they had to get water, but they didn't have like electricity, right? So how are you going to move water? So what we need to do is we need to basically create a connected line of fluid from this reservoir to somewhere below the surface of the reservoir, and that will create a hydrostatic pressure differential, and then flow can actually go between those 2 points. So what it'll end up being is flow will go, say, through this tube into this beaker here. So right now the tube is filled with air. So if I dip that in, obviously it doesn't do anything. So what we need to do is fill the tube up with water. So if I fill the tube with water first, I have one end of the tube in our sort of reservoir, and the other end here. So down here is at a lower level than the top of this reservoir. So the hydrostatic pressure, there's a hydrostatic pressure difference, so then the water will flow. And this will keep going until you drain the entire reservoir. So it seems like magic, but it's not, it's just fluids. So what we're gonna do is, here, let me just do this. So we're gonna analyze this using Bernoulli's equation, and then we're going to experimentally measure this flow rate. So I have 2 different diameters of tubing to show you the effective diameter. So this is a small diameter tubing, and if I show you again, this is what our flow rate looks like. So we're going to measure this flow rate. So that's a small diameter of tubing. And this is a bigger diameter of tubing here. So I just need to get this filled up with fluid. Okay, so the bigger diameter has a much higher flow rate, as you can see. So see how much faster it fills up? So it's the same, the driving force behind this fluid's motion is the hydrostatic pressure difference here. There's no pumps, there's no anything. So we're just using basically gravity to drive this flow. So the difference between the 2 diameters, the only difference in that case is the differing frictional losses in the system. So that's why the higher diameter will have lower, you might have seen a higher diameter pipe has lower pressure losses, so that's why. Okay, so I'm going to set this problem up and then we're going to do some analysis here. And the math will get a little bit ugly, but the end demo will help us motivate this. Yeah.
Does the siphon work if you just put the tube in on
The tube, what? Sorry?
if you don't have any atmosphere, does the siphon work even if you don't have a continuous flow?
Yeah, so the atmospheric pressure doesn't actually matter at all. We'll see in the analysis. It's all about the gravity. So the reason atmospheric pressure doesn't matter is because the top of this reservoir will be considered 1 point in our Bernoulli's equation, and the discharge point of the tubing is another point in our Bernoulli's equation. So if you assume both of those points are at atmospheric pressure, that cancels out in the equation. Yep. Oh yeah, I'm not sure how those work, but I can look that up and let you know. So they can't be that complicated. So cool. Okay, I'm gonna do this problem then on our computer, and then we're gonna measure the flow rate ourselves. Okay, so let's draw a sketch here. So we have a very big kind of reservoir of fluid. And our tubing is going to be connected like this into the reservoir. basically our sketch of this system. So this is a free surface of this reservoir. So I'm going to choose point 1 in the equation to be the free surface of the reservoir, and point 2 be sort of the discharge point of that tubing. So we'll write our extended Bernoulli's equation. So I'm grouping all of our losses just at this stage into some delta P losses. Now, you could take, say, point 1 to be the entrance point, like this. But the issue is the velocity there at the entrance point is an unknown. So the reason I picked point 1 to be the free surface of the reservoir is so that we can say a couple of things. Well, one, the velocity there is unknown, and the pressure there is also unknown. But at 1, the pressure is equal to atmospheric pressure. And at 2, since the water coming out of this tube is just exposed directly to the atmosphere, it's also going to be at atmospheric pressure. So basically, P1 equals P2, so those will cancel out, like we talked about. So the atmospheric pressure, if there was a vacuum in this room, it wouldn't affect, I mean, it would affect a lot of things, including us, but it wouldn't affect this. The other thing that is convenient about choosing point 1 here is that if this reservoir is very wide, which I've picked my widest Rubbermaid from home, we can assume that V1 is 0. So even though this thing is draining, by definition, it has to have a very small velocity. But if we say V1 is approximately 0, so say this was a big lake or something, and you're trying to drain the water out of the lake, you can assume, say, the free surface is 0 velocity. So if I picked a smaller, like if I picked, say, my water bottle as the reservoir, we would have to sort of track the velocity of that reservoir because that might have some kinetic energy that's moving that we need to account for. So if we do this, this is the simplest way. Okay, so we get, so rho g z1 minus z2 is 1/2 alpha 2 rho v2 squared, plus we also only have one sort of branch, and I mean one diameter in our system, so we don't need to sum the losses, we just have the one loss. So FL over D rho v2 squared 2. We will have a couple of different losses though. So the left-hand side is basically our driving term. So our driving term, without any losses in our system, we would convert all the driving energy into kinetic energy at the outlet. But we have frictional losses in our system, so that's where some of this is going. So those, not all of it is going into kinetic energy of our fluid. Some of it's getting lost to friction. Okay, so let me see. I'm going to finish this up before I go back over there. So the friction factor is complicated here, right? Let me talk maybe about the KL first. So we have an entrance loss here as water is kind of flowing in. We also have a loss in this bend. The rest of this is basically just straight pipe. And I don't think we have anything in this Cengel table about, say, an atmospheric discharge loss, so we can't really account for that. So I'll go to the table now to get our loss coefficients. So we have a pipe inlet because the flow is going into the pipe here, like this. So if I kind of hold the tube just in the reservoir without getting too close to the bottom, So the reason I'm not getting too close to the bottom is like there. We start getting effects like this. So yeah, you want to hold it, I guess, decently far away. I think that it's probably a couple of these assumptions are violated, but we're still going to use this anyway. We have a pipe inlet loss there, KL of 0.8. We also have our bend loss. So this 180-degree return bend. So that thing is the tubing that we have is definitely not flanged, but I'm going to just use the flanged KL anyway from this table. So if you see here, the flanged KL is 0.2 and the threaded KL is 1.5. So there's a much higher loss in a threaded 180-degree bend. I think that's because of interactions that are created, say, internally at the joint. So the flange would be something like this. They butt up there, and then there's a gasket that's put in between the. So there is some flow disturbances created here before the bend and also after the bend. I think it's worse for threaded connections, which is why the threaded loss coefficients are all higher. But so I'm going to take 0.2, which is a little bit conservative there. So that's the losses I'm going to consider. So KL. So I think that was 0.8 for the entrance plus 0.2 for the bend. Any questions on the minor losses there? Hmm? So that the exit losses in this table are exiting, say, back into a tank or a reservoir. So I think that there is some sort of loss there, or some sort of, the flow definitely changes as it leaves that. But these are all, see this pipe exit, a reentrant? That's if it was discharging like back into a tub of water. So this whole thing in the gold there is all water. So you would actually get like swirls like this, right? But we don't really have this situation here. So if you happen to know the loss coefficient for this discharge to the atmosphere like this, we could account for it, but it's not in this table, so I'm just leaving it out. Does that answer your question? Okay. So yeah, if we were trying to pump into, say, the bottom of a tank, then we would have something like this, where you have a reentrant type loss or one of these edges losses. What is a good question? Any other questions on the minor losses? Yep.
So at the end of the siphon was like put like at a fixed
Yep.
position and the water level rise at a certain point, you would have to account for it feeding back into a tank.
Yeah, then you would have an entrance loss. The reason that I'm discharging to the atmosphere there is to make my assumptions much easier to point to, because then like if I'm discharging back into, say, which the siphon will still work if I do that way, because there's still a hydrostatic difference. But I just want to make the assumptions easier, basically. Yep.
Is V2 the average?
Yes. So extended Bernoulli's equation is always in terms of averages. So if there's an alpha in your equation, that's to correct for the fact that we're using averages, not like a maximum or streamlined velocity. Any other questions? Okay. So this is the reason that this type of problem is considered a little complicated. Because the friction factor here, so if we use the Holland equation friction factor, we can explicitly find the friction factor using the Holland equation. So we don't need to iterate. We don't need to sub-iterate. So you can verify this kind of substitution into the Holland equation here. Sorry, 1.11. So this whole thing is just the friction factor. We have L over D, rho V2 squared over 2. So this is why I would say this is moderately complicated. So we have V2 here. It gets even more complicated when we're looking for diameter. So our unknown there has our unknown parts, because the diameter of this system is fixed. So D isn't an unknown. So we have, I'm going to write the V2s in red because that's our unknown, right? To determine the flow rate of this system, we know everything else except V2. So we can determine the other things by basically measuring this. Okay, so I'm going to measure this. I'll show you the measurements. So the L in our major losses there is just basically the length of tubing we have. So I think it's roughly 17 inches here. So if we just measure the straight length here like this, so it's roughly, sorry, this tube sucks. This tube sucks. 17-ish, good enough. 17 inches of, so that's L. The Z1 minus Z2, so remember 1 is the top of the reservoir and 2 is the discharge point. So this definitely varies. If I move this, it changes that Z1 minus Z2. But I measured this earlier, and I guess if I go to about the top there, see, I measured this earlier, but I was using a different beaker. Does someone want to help me measure this? Here, okay. So if you take, so measure from the top of this water line to say the top of the beaker, and I'll try and hold it at the top of the beaker.
Top of the beaker.
Yeah, like
You're getting
6.5.
Okay.
Okay, that's what it was earlier. So that's good. I can reuse my solution. Okay. So I'll give you those kind of measurements and then we'll do the flow rate measurement. So this is a big kind of ugly equation that used to be really difficult to solve, but you guys can just put this into your computer and solve it. So consider yourself lucky, I guess. So L is 17 inches. Z1 minus Z2, 6.5 inches. Again, that's the discharge point of the tubing versus the height of the water. Okay. So for example, I solved this using these measurements in Wolfram here. So this is the input. This is the whole equation. So that's rho g Z1 minus Z2, 1/2 alpha rho V2 squared, and then the friction factor thing. And you can see the x here is the V2. So we basically have one equation, one unknown, so we can solve this numerically. So they used to have to solve this by hand, but we're going to just use the modern solution, which is use computer. So that gives V2 equals 0.732 meters per second. So that's what Wolfram told me. Okay, so that means our volumetric flow rate is V average times the area. So this is about 0. I think this is like 0.1013 liters per second. Someone have a calculator, they can check that because my numbers changed from when I did the solution. This right, just plug this in right here. This box. I think it's roughly 0.013. Anyone? Yes? Did you do it in liters per second or in meters? Is it 1.3 at the end of all the zeros?
Yeah, yeah.
Okay, we'll call it 1.3 then. So that was probably in meters cubed per second. Okay. So now I'll have a couple people time this, and then we're gonna check the flow rate of this. I can't time it on my phone. Yep.
Let's say hypothetically, if you were to like put gas, so you weren't able to dump the whole thing in, like suck on it to create that pressure.
Yeah. So in an emergency situation, usually you put this into a gas tank, and then yeah, that one.
Would that be technically your delta pump?
Delta pump.
Yeah, like you like that initial.
Oh, yeah. You could calculate. No, it's a good question. So say you wanted to calculate the basically amount of suction you needed to provide on this. You could do that with Bernoulli's equation. It wouldn't be like a delta P pump. It would be you would get basically the pressure that your mouth needs to be in order to create that flow. Yeah. Yep. Yeah. So guys, just give me one sec. So he asked a good question. So he said, is the capillary effect involved at all? So the capillary effect would be like, since this is a small tube, if I stick this in, we would expect a small rise, but this tube is already big enough that the capillary effect isn't really, the capillary effect is for very small diameter tubes. Okay, so I need a couple, maybe everyone around here to maybe time this. So I'll tell you when to start your timer, and then stop your timer when it hits the 500 milliliter mark. So we're going to basically just do volume over time to get the volumetric flow rate. And the bigger volume you do in that, the less error you get. And there's going to be a lot of sources of error here. Okay, so you guys ready? Okay, 3, 2, 1, go. Okay, so I'm just trying to hold this so that I get a negligible sort of entrance losses. Go to the 500.
Using your phone right now.
So by the way, we did assume this to be turbulent, right? So if you verify with that velocity, you actually get turbulent flow even at this very small diameter. Okay. What did you guys get?
38.
38, okay. So that was 500 milliliters of liquid. So if you do that, if you do 500 divided by 38, you get something like that, I think, in terms of liters per second. It's close. We'll probably have like a 10 to 20% error with the assumptions we made, but I hope maybe this helped you understand like the different assumptions that we're making in this problem. Yep. You cannot bring something like this into an exam, no. Okay, any other questions about this? Yep.
Does the friction from major and minor times help to create a laminar flow? This slows down the velocity.
It could, yeah. In certain situations, it could. Any other questions? Okay, so that's everything for today. Thanks, everyone. Thanks.